Hi everyone. This is machine learning with Python course called MLUP-101, and the module number is 6 and part 1. This is advanced machine learning, and so this is the 10th session. We have completed 3 weeks. So let us give a handle to Jamie, who is the instructor and has been doing a good job. Very well organized, I believe. It's just a matter of understanding what it is, what is module, what is part one, part two, what is session, and how he is handling it. So, Jamie, take over from here and go ahead and help everyone in the study circle. Yeah, go ahead.
Yeah, thank you, and uh, welcome to this machine learning using Python module 6.1. This is session 10, and now we'll be starting with advanced machine learning topics, meaning that what we have learned will be doing something more in depth with the things that we have discussed, like linear regression and stuff. So, first, the objective for today's session will be we'll start with foundations of machine learning or the categories of ML, then discuss about the supervised and the unsupervised learning, discuss the cost function and how the optimization algorithms like gradient descent helps us in optimizing our model, minimizing the cost function, and then we'll be using the scikit-learn's regression to build a model. We'll also deal with overfitting and underfitting and what to do when they appear. So these are the only topic. These are the ones that we'll be covering in this session, and this will be the whole for module 6. So for module 6, there is also the further discussions will be taking place about random forest and the boosting techniques, and also the last point, as it states, the feature selection using machine learning models. So let's get started with machine learning. So this is the recap that we have always been using about AI and ML. So AI helps the computers to think and act like human and perform particular tasks. When we do it with the help of machine learning, we teach the task first and make the model learn. And when there are some complex tasks or complex insights to be gained, deep learning is often used in order to get those complex insights. You can see the relation between the AI, ML, and DL with the help of the diagram that is shown, Venn diagram. So this is the ML, and these are the ML categories that we have often referred when we are talking about ML. So we have these ML categories: supervised, unsupervised, reinforced. Supervised means we already have the output and we are trying to make the model learn and have the highest probability for the likeliest of the outputs. Then in unsupervised, we do not have the output and we let the model tell us what are the hidden patterns beneath the data. Then comes the reinforced learning, which works on the reward based system, and we penalize the model if we want the certain behavior not to occur.
So, Jamie,
Yes.
model doesn't tell, data is interpreted, right? So,
Yes.
so make sure that model doesn't tell anything. It is the data which tells how the model should be. So
Yes.
that portion is unsupervised. Without supervision, data pattern will tell as what the model should be. Okay.
Yeah.
Okay, good.
Yes, so the correction regarding my take on the unsupervised learning, it's the hidden patterns under the data that is discovered by the model that helps us. So then, of course, they have these subcategories for classification and regression, one for discrete classification, and then comes the regression for continuous values. Then in classification, we have binary and multi-class. Binary is 0, 1. Multi-class is more than two classes. Then comes clustering, where we group similar kind of data together depending on the relationship they have. Then comes association. We associate one data with another with a kind of uh, relation. Then comes the dimensionality reduction, which is basically a technique to in feature engineering, where the number of features that are used for training the model or used for the model are reduced, and the most efficient ones are used while also preserving the originality of the data set. So there are two topics that we can discuss is the statistics, which tells us about the data, how to interpret, how to present the data, how to organize the data. And those things help us to visualize the data as well, to make inferences and make predictions based on the data that we have. Now, on the other hand, we have objective based machine learning, which is where the uh, computers or the model learns from the data, gives insights, and helps us make the predictions as well. And with time, we are expecting this model to also improve and adapt with time. And if we want to make it more generalized, then we can, for a broader use, we can do that too. So, supervised learning, the data sets have the values of the input variables and the corresponding outcome variable. The algorithm learn from the training data set and predict the outcome variable for the new record and values of the input variables. Linear regression and logistic regressions are examples of supervised learning algorithm. Then comes the unsupervised. The data sets have only input variables, but not the output variable. The algorithm learns the structure in the inputs that are given to the model, and clustering and factor analysis are the examples of unsupervised learning. So how so we have seen which are the types of the machine learning categories, but how do they actually learn? So basically, what how in supervised learning, how they learn is whatever output we have, they make a prediction on it based on the probabilities. It's always a probability. They are not certain, but high probability gives us the confidence that this is closer to the output that we are willing to have. So there is a difference between the outcome that is already there and the predicted outcome by the model. So that predicted outcome, if we see, is the difference between the predicted outcome and the desired outcome that we have, or the actual outcome that we have, is called the error. So for a function where n total number of records, there is h of xi is the predicted output and yi is the desired output. So the sum of squared errors is given for the regression models are given by 1 by n and the summation of all the errors that are occurring for all the records from I equals to 1 to n. So this acts as a loss function for regression models. So for minimizing the loss function, we use the optimization algorithms like gradient descent, Bayesian optimization, etc. So, we have already been familiar with the simple linear equation where yi is the dependent variable and xi is the independent variable. So, in the first expression, which is mathematically represented, yi equals to beta 0 plus beta 1. So, beta 0 is our intercept and beta 1 is our coefficient plus epsilon I, which is which is nothing but the error. So intercept, just to recap, intercept is nothing but the least amount of uh, sorry, let's say there are the values of x are 0. So what will be the value of y when x equals to 0? So that is the value that is represented by intercept. Then coefficient is nothing but every 1 unit change in x will be represented by that coefficient. So this is about the linear equation, but there is a predicted value also. So predicted value is represented mathematically as a yi hat equals to beta 0 hat plus beta 1 hat xi. So beta 0, beta 0 and so as we are using hat representations, and those are for the estimated values. So the error will be given by yi minus yi hat, which will be further for the values of yi hat. You can see that the error term is substituted. So the total error or the means squared error will be given by 1 by n, capital N, for the n number of records and the summation of all the differences between the predicted and the between the actual and the predicted values whole square. For the records I equals to 1 to the total number of records n. So the gradient descent finds the optimal values for beta 0 and beta 1 that minimizes the loss function using the following steps. Now, before going to steps, let's just look at the graph first. So the graph, you can see that gradient is nothing but the slope. So the slope goes down. So when it goes down, it reaches a value where the error is least, or it's the minimum error that is possible. So that minimum error is something that we are trying to find for us. So going to the steps, randomly guess the initial values of beta 0 and beta 1, or the intercept and the feature weight or the coefficient. So as we move forward in this session, the bias, it will be the intercept will be called as bias, and the coefficients that we used to say will be called as weights simply. So calculate the estimated value of the outcome variable yi for initialized values of bias and weights, and calculate the mean square error function MSE. Then adjust the values by calculating the gradients of the error function. Now now that you can see that the values that are used for beta 0. So there is a new term called alpha. Now, alpha is nothing but the learning rate. So alpha kind of sets up a space for a pace for the machine learning model to learn, or rather a speed for the machine learning model to learn. Now, alpha's value can also uh, make the model good or worse depending on the alpha value that we have given. As if you try to give the model much higher pace, then it won't learn the data very well and it will perform poorly. The same goes for uh, having a very low rate of alpha, where the where if you give a very low value to alpha, then the model will start learning the very minute details that it shouldn't have learned, and the model will not be able to generalize the data set well. So alpha is like having a balanced value which also learns nicely as well as learns quickly. So the partial derivatives of the MSE function finally is given by for beta 0 and beta 1. As you can see, it's for beta 0. So it's for the error with respect to beta 0. So minus 2 by n, and the summation of actual minus predicted values for all the records. The same goes for beta 1, minus 2 by n, difference between the actual and the predicted values into the record or the observation of the data set xi for all the values of within the data set. Now we repeat these steps 1 to 4 that we have seen over here. Randomly guess the values of beta, the intercept or the bias as well as weight, calculate the estimated value, then calculate the mean square error function, and adjust the values of bias and weight by calculating the gradients of the error function. So the values of beta 0 and beta 1 at the minimum cost points are best estimates of the model parameters. So the one thing regarding error, that either the error stops going down, or the value between the errors can be very small in order to not just simply ignore it. So in both the cases, we can say that we have found the minimum cost. So developing a gradient descent algorithm for the linear regression model. Now we'll be using a dataset for for advertisements. Now, and this dataset basically on this dataset we'll basically do is will we have the expenditure for the ads run on TV, radio, and newspaper. What we'll be trying to predict is the sales depending on these three variables, which is TV, radio, and newspaper. So we are simply using the dataset and reading the dataset. The first few values of the dataset looks something like this. You can see that for the zeroth index, the TV, the radio, newspaper sales and stuff.
back?
Hello?
Can you go back and show the data set?
Yeah, I showed it.
Yeah, yeah. No. So, what is the relationship you are correlating here? Is it the advertisement is
So these
different?
are the these are the values of uh, the money that was spent on TV, radio, and newspaper, and the relative sales that they got for it. So the sales are the things that we are trying to predict, and TV, radio, and newspaper figures will be our independent variables that we'll be using in order to predict the sales that we have.
Good. Good. That helps.
Yeah. So, uh, as also as mentioned that we'll be using TV, radio, and newspaper in that order and try to predict the sales. So, before that, we'll be using a standardization in order to standardize values in the regression model. So, a common technique known as feature scaling, specifically standardization, will be used to transform the variables in a data set so that they have a mean of 0 and a standard deviation of 1. This process is beneficial for uh, machine learning algorithms, particularly those that are sensitive to the scale of the input features. So in optimization algorithms like gradient descent, the goal is to minimize the error or the cost function. So we move in the opposite direction of the gradient descent to reach the optimal parameter values that minimize this error. It is important to convert all variables into one scale, and this can be done by subtracting the mean and each value of the variable and dividing by the corresponding standard deviation. So that is so this is what we are doing, and the simply putting it into the um, code, the mathematical representation into the code. So will be using the numpy array and get the y value, deduct it from the mean, deduct mean from it, and divide it by the standard deviation. We'll do the same for the x values as well. We'll be doing it with the help of the lambda function and use the records, and we'll be doing it column wise, and that is the reason that x's value is equals to 0.
Before you move,
Yes.
so both sales DF and x equal to sales DF, y equal to sales DF. You mean
Yes.
we are in the same table or same array?
No, no. So sales DF is same, but the columns are selected from the sales DF.
Okay.
So TV, radio, and newspaper will be acting as the X values for independent variables, and sales will be given as Y values.
At the bottom again,
Yes.
you are saying something like array. It's a numpy
Uh,
array,
yes.
and it says y minus y mean.
Yes.
Whatever sales is there, if there are 10 sales, then you are having 10 sales, mean of the 10 sales.
Yes.
Okay. And what is the y?
Standard deviation.
So you are taking a difference of, that is the deviation from the
Yeah,
mean.
basically we are standardizing the values
And
for X and Y both.
so you are taking one standard deviation as the measure for the one, that is sample value minus the mean
Yes.
divided by one standard, right? One variation. One.
Yes. No, we are basically bringing them in the one deviation method. So mean of 0 and deviation of 1.
Yeah. So we are measuring, trying to get samples and see how much variation they are based on if it is one standard variation.
Yes.
And what about X?
Sorry.
What about X? Lambda is just a function, right? Python function,
Yes.
which
Lambda is an anonymous function. It's from Python only. So
so
uh,
so you're applying
we are,
Python.
yeah, we are standardizing the values of x just the way we did it for y, and x we are doing the standardization in column wise. So that's why the x's value that it takes is given as 0.
Okay. So what you are saying is X is the dependent or
X is the independent variable.
independent. So all independent variables that you are using, like the TV, the radio, news,
Yes.
those are in column,
Yes.
and there you put X is equal to 0. What does that mean? That means the row, it's per row. You will start increasing from 1, 2, 3, 4 in rows.
No, no, no. X is a value. So there is this thing that X is equals to 0 means the operations will be happening column wise. So TV, radio, and newspaper that way. But if X is equals to 1, then the operations will be happening row wise.
Okay.
So index 0, 1, 2, 3 that way.
Okay. So this is column wise.
Yes.
And in the column wise, you since you are it's a lambda function, you don't care whether what it is. It is TV or radio.
Yeah.
But
Basically bringing all the values into a single scale kind of thing.
and basically record means that particular TV record.
Yeah. Yes.
Record means
Particular.
particular radio record. Record
Yes.
and the means of those are different for both. Different columns is different means
Yeah.
and different standard deviation. Okay, got it. Got
Yeah.
it. Yeah, you can move on now.
Yeah. So we'll be implementing the gradient descent algorithm now. We'll be doing it in the 4 methods that are present. So method to randomly initialize the bias and weights. Bias intercept. Weights are your coefficients. Then method to calculate the predicted value of y and y given the bias and the weights. Then method to calculate the cost function from predicted and actual values of y, and the method to gradients method to calculate the gradients and adjust the bias and weights. So let's start with method 1. So we'll be importing the random in order to use it further. So we'll be defining a function called initialize, and initialize will be taking the dimensions that we are trying to get. So dimension is nothing but the number of weights to be initialized besides the bias. So we have 3 things which are TV, which is TV, radio, and newspaper. So we'll be using for 3. You can see that we are using it for random seed of 42 in order to get the we reproduce the uh, result just in case if we want to do it or refer it back again for this seed value.
So you mean if the seed value is 42, you will get the same result every time
Yes.
for a given data set. Okay.
Yes.
And if
So
we change it,
basically, what it does is, let's say we shuffle, and if we give a value of any number, then it will be recognized by that number. So it's a same thing that we have used in the previous session for random state.
so it's a
So
pseudo random. Actually, it's not totally random. You only set the seed
yeah,
as
we are trying to control the randomness of it by giving it a number and always reproducing the same set of records with the help of the number.
thanks.
Yeah. So initialize the value of W for using the numpy random and the randomness for the dimensions, and in the end returning the value back for the bias and the weights. So when we use this as said that we are using it for three dimensions, TV, radio, newspaper, we will be giving the value of 3. So the value that we get for the bias, as you can see, is 0.639 and so on. For the weights, for TV it's 0.37, for radio is 0.95, and for newspaper it's 0.73. Now we predict the values from the bias and the weights. So here we'll be using the matrix multiplication. Uh,
Can you just run the previous interpretation? So I'm trying to understand through execution. Is it,
okay, wait.
yeah.
So this is the data set that we have uh, read, and these are the first few values for it. Then comes the x and y uh, variables being assigned for the column values, that these and these. Then we standardize these values for x and y both, and for x we are using it for the column operations. So the first thing that we did was to randomly initialize the values of bias and weights. So we defined a function, then gave it the seed value of 42, our bias and our weight.
So how we got the seed value of 42 means
No,
from
no,
here.
seed value is given by us. So 42 is something that before there is something called as a random state also. So 42 is something that's conventionally used across the community. So 42 is just the go-to number for having the seed value. It's given by us, but you can also give it for you can also give it 100 or 101 and so on, as far as you know that which ones are resulting. And if you
Okay,
want to reproduce the result, you can again go to that seed value just in order to use that those results further.
okay,
Okay, so
yeah,
when we run this function, we get the bias and the weights of it. So remember that we gave it for three columns. So the bias that we get is this value. Then the weights for the TV, radio, newspaper, 0.37, 0.950, and 0.731.
Put it this way,
okay,
this is a trial and error, right? It's like,
Yeah, we are randomly initializing the value just in order to then later get to the best values.
yeah. So you have to
Yeah,
start somewhere on the curve. You
yeah.
think that 42 is a good, because the random number could be 1 to 100 or 1000, I don't know what it is. The generator must be having 1 to 100, so 42 is some random number we have chosen.
No, no. 42 is the number that we are giving, but it does not have to do with the weights, but the records that are used in order to produce these numbers of bias and weights.
Okay. So it's a mathematical number, just number, some number given to you. Yeah,
Yeah, it's just a representation of all the records used. That's it. You can just imagine it like a variable name or something to be used for a particular kind of records, but just in form of only numbers. Next was to predict y values from the bias and the weights. Now we'll be using the matrix multiplication over here, and I'll directly go to the function definition while be using it. So we have bias, weights, and the input variable as the arguments when we define prediction y or a predict y function, which will return the bias plus the matrix multiplication of the input variables and the weights or the coefficients related to it. So basically the reason to do it is because the x is a column. When we transpose the matrix, it becomes rows, and the rows will be easier to multiply in a dot product after converting it from column to row. So x is transposed, it becomes a column, and column will be multiplied with the weights in order to get the values for the coefficient and the independent variables used for the x. So the y hat is the predicted values of x for the bias, weight, and the x values given. So the output that we get was the array, numpy array of 0.323 and 1.707, then 2.8 and stuff, and till the minus 0.768. So this matrix multiplication operation allows us to efficiently calculate the prediction for all the input samples in one go, which is the essence of using the matrix multiplication in regression models. Now calculating the mean square error. So we have already used it in the previous slides for the for calculating the MSE. We calculate the difference between the actual and the predicted ones, then calculate the square of the residuals or the error that we got from the difference that we calculated, and the sum of it over all the records, and dividing it simply by the number of observations. So translating this logic into the code, we will be defining a function called get cost. It will be taking the actual values of y and the predicted values of y, denoted by y hat, and we'll be storing the difference in the y residual. So the matrix, you can see the comment after the y residual. The matrix multiplication with self will give the square values, then take the sum and divide by the number of examples to calculate the mean. So we calculate the mean and return it to the function called. So when we use get cost for the values that we have used initialize for value 3, then use the y hat for getting the predicted values, and getting the cost on it, we got 1.53. So we calculated the cost function, which is a mean squared error on linear regression models. Now updating the bias and weights. So for the intercept or beta 0, these are the formulas that we have already seen in the previous slides. So how we will be updating is use the define a function called update beta, and which will be taking the parameters as xy, y hat, the bias and weight, or which will be denoted by B0 and W0, and the learning rate, which is defined by alpha in the formula. So the update beta function is defined, and you can see the parameter values it takes. We we calculate the bias and weights for it, update the values of current bias and save it in B1, and do the same for the current weights and save it in W1. So we got the current values of the bias and weight, which are nothing but the intercept and the coefficient values. Now using these, so we use the initialize function again, print the values, then use the predicted values of y and store it within the y head, and also get the updated beta values and store it in the B and W denoted by bias and weights. So you can see that after initialization and after the first update, the difference in the bias and the weights values. You can see that it's a 0.01 kind of difference in the bias, and for the weight, it's yeah, similar kind of difference of 0.01 or 0.02. Now, the learning rate, as we have been we have now actually used the learning rate in terms of this formula. So learning rate that we have used is 0.01 over here. So how it impacts the model while learning and stuff. So first is the step size. As I said that learning rate defines the pace of learning the dataset by the model. So the learning rate determines the size of the steps taken in the parameter space during optimization. A larger learning rate means larger steps, while a smaller learning rate means smaller steps. Now it has the size that we give for the learning rate or the alpha value. It has an impact on the convergence. Convergence is nothing but the model learning the task. After that, the error cannot be further reduced and stuff. So and the model learns the data completely. So that is what we call as convergence. So there is an impact on the convergence of it. So a higher learning rate may lead to faster convergence. That is, the algorithm reaches the minimum of the loss function more quickly, but it may also lead to overshooting the minimum or oscillating around it. Conversely, a lower learning rate may result in slower convergence, but may be more stable and less likely to overshoot the minimum. Now, even though the step says that the lower learning rate can help, but a lot of making the learning rate very low can also impact. Now, third is tuning. So the learning rate is a hyperparameter that needs to be tuned during the model training process. It's often determined through experimentation where different learning rates are tried and the performance of the model is evaluated on the validation set. Now, the grid search or the random search, the common approaches to which are the common approaches to finding the suitable learning rate include a grid search, trying a predefined set of learning rates, or the random search sampling learning rates randomly from a predefined range. So techniques like adaptive learning techniques, which are adaptive grading or RMS prop or ADAM, these are dynamically adjust the learning rate during training based on the gradient's history. Now these are the approach for a grid search and random search are. Then comes the regularization, which is the learning rate can also interact with other hyperparameters such as regularization parameters and affect the model's generalization performance. Hence, it's essential to consider the learning rate in the context of other hyperparameters during model tuning. So basically, these are the things that are affected by the learning rate value that we use. So uh, we are trying to find the optimum values for the bias and weights, which we can use for our linear regression model. So we use the updated values for the last time we saw was we used the updated values of bias and weights. So bias and weights needs to be done iteratively, and until the cost is minimum, it can take several iterations and is a time-consuming process. So there are two approaches to stop the iteration: run a fixed number of iterations and use the bias and weights as optimal values at the end of these iterations, or run iterations until the change in cost is small, that that uh, that is less than a predefined value. So which can be 0.001, for example. So basically what we will be doing is defining again a function which will be called as a run gradient descent, which will be taking the learning rate as a parameter and the number of iterations. Now this run a run gradient descent function, and that will be using the initialize, prediction y or predict y, get cost, and update beta as the functions that it automatically invokes. So inside the method, there will be something called as gradient descent iterations df, which keeps track of the cost every 10 iterations. And the default value that we'll be using for learning is 0.01 and 100 for number of iterations. So we'll be iterating through it for 100 times at the learning rate of 0.01 and saving the values of those things in gradient descent iterations df. So just in case this explanation was confusing, basically what we are trying to do is define a function which runs or iterates through it, saves the value of it for the number of 10 for every 10 iterations, and also save the cost of it in a data frame called GD iterations TF. So we initialize with the bias and weights. Iteration number will be initialized to with 0. Then we'll be using the iteration and cost as the columns for it, and the result index will be initiated again to 0, and we'll be updating it through the for loop that we'll be using for the number of iterations. Just a second. So from the for loop, we calculate the predicted values of y, calculate the cost, save those, save the bias and the weights, update and calculate the values of the bias and the weights from the update beta function. As you remember that we'll be invoking these uh, functions: initialize, predict, get cost, and update beta. So with the help of update beta, we'll be updating the values of bias and weights, and using the if statement just to save the records, printing the final estimate for the bias and weights, and then printing the values that we get and return those values as well for the calling function. So when we use it, you can come on the top right of it, or right of the screen. So the data frame, bias, and the weights are used for run gradient descent, and x, y, and the alpha value of 0.001 is used, and the number of iterations that we give are 200. So the final estimate after running for the number of iterations as 200, we get these values, and these are the top 10 values that we get for the GD iterations TF, with the iterations and the cost associated with the iteration. So we'll be also plotting the cost function against the iterations, just in order to get a visual clue of it. So we'll be using the matplotlib and cpon, and calculated using the GD iterations and the number of iterations and the cost that is associated with it. So when we do it, you can see that the the co the cost associated on the y, and the number of iterations on the x-axis, and with the number of iterations, the error is also going down. So as the slide says, the weights are standardized values, and we have used the standardized values of y and x. So which means that the one standard deviation change in TV spend, the sales revenue changes by 1.5 standard deviations, and so on. So from the graph, we are checking whether we got the minimum point or not. So we'll be using the learning rate df1, using the bias and the weights values on the run gradient descent function that we just used, and the bias and weights that we got is bias for 2.77, and but look at it that it's into 10 raised to 10 minus 16, and the other ones are the weights for 0.75, 0.53, and minus 0.004. For alpha value equals to 0.001, or the learning rate equals to 0.001, the bias that we get is 0.011, and the weights are 0.74, 0.52, and 0.01 for TV, radio, and newspaper in that order. So when we compare the learning rate of 0.01 and 0.001. If you only look at the graph, you can see that uh, for the learning rate value of zero point zero 0.01, it learns very quickly compared to the learning rate of 0.001, which is denoted by orange. So for us, the value of learning rate will be taking is zero point zero 0.01. So uh, we uh, we saw it till the initialize the till we defined the initialized function, and which took the number of dimensions it take. We are going for, which were, so basically okay, let me just start it again. So we read the data set, saved it with sales df. From sales df, we created the x and y inputs. We standardized those values, and we'll be using the four methods, starting with a method of randomly initializing the values of weights and bias. So we wrote a function called initialize, which took the number of weights that it was supposed to go for. We for our case it was 3, so we did it with 3, and the values that we got for bias and weights are these. Next, we predict the values of y from the bias and the weights. So we, because we are trying to predict the values of y based on bias and weights, we defined a function which gave us the, which returns us the values of y based on that. So when we got the predicted values saved in y hat using the predict y, these are the values that we got. Then we checked for the cost function, which we'll be using is mean squared error. In order to get the mean squared error, we import math. We we define a function called get cost, which basically calculates the y residual value, which is nothing but the difference between the actual and the predicted value. So when we do it for the uh, predicted values of y and calculate the cost function on it, we get the cost of 1.53. Now we update the values of bias and weights using the defining the values of defining the function of update beta, which will take these following parameters, which is x, y, the predicted values of y, the current bias, current weight, and the learning rate. So for using the learning rate of 0.01 on this update beta, these are the values that we get. For these were the initial values, and these were the values after the updated values of bias and weights, and the learning parameter as well of 0.01. Now we want to find the optimal values of bias and weights, for which we define this run gradient descent. So first we tried it with the alpha value of 0.001 and the number of iterations of 200. So the final estimates for bias and weights that we got were 0.42, and the weights were these for TV, radio, and newspaper. We saved those values in the gradient iteration DF. So these are the values as per the iterations. Next, we plotted the graph for the number of iterations and the against the cost. So you can see for the x-axis number of iterations are there placed. It's not a cost or MSE. The cost or MSE is on Y. So this is the graph that we get starting from 1.5 as gotten here and reducing further. Next, we tried it with the number of learning rate of 0.01 and the number of iterations of 2000. The same goes for learning rate of 0.001 and the number of iterations for 2000. So when we compare these values of different learning rates, but the same number of iterations, this is the graph that we got. And you can see that why we chose to go for alpha value of 0.01 as it learns quickly, as it minimizes the cost quickly compared to the learning rate of 0.001. Now, as you can see that till now we are using only numpy in order to build our linear regression model. Now we'll be using the scikit-learn library in order to build the regression model. So we used a numpy in order to get the details about how the linear regression stuff goes and works, and how the learning parameter, learning rate affects the way the of the cost and stuff. So, but scikit-learn already has some of the predefined algorithms for linear regression, classification, clustering, and stuff. So we'll be using the scikit-learn. So for building the machine learning model on or the linear regression model for our from scikit-learn, first we have to identify the features and the outcome variable. We already know that. Then we split the data set. We build the model using the training set, predict the outcome with the test set, and compare the predicted and the actual values using the mean absolute percentage error or MAPE and root mean square error in order to know the accuracy of the model for the predictions it has made. So we import scikit-learn's model selection and use the train test split in order to split the data set that we are working with. We are splitting it into 70-30 because the test size is 0.3 and the random state value is 42. So the values within the X train is 140 and for X test is 60. So building a linear regression model, we'll be using a linear model from the linear regression for the scikit-learn. We'll be naming it, we'll be saving all the values that linear regression gives us in linreg variable. So linreg will be used in order to fit the X train and the Y train for it. For getting the values of the intercept and the weights, we will use linreg and the intercept and in the end the underscore in order to get the bias value, which is 2.7, and the coefficient values are given by dot coef array. So it will give us the array of the coefficient values, and it's the same order that we have used TV, radio, and newspaper. Lastly, we'll be zipping, or we'll be creating a kind of dictionary for the values that we get for the column from using the zip function of Python. So basically what we are doing is associating the values of TV with the linear regressions coefficients of the first, second, and third values with the TV, radio, and newspaper. So the functional form, or the mathematical representation of linear regression, is given by yi equals to beta 0 plus beta 1 xi plus the error on that record. So when according to this, the sales formula, or the sales that we get, can be calculated like this. So for every change of, sorry.
This is the model.
Yeah, this is the these are the values that we got, and we can basically predict using this.
Yeah. So this is the model right now.
Yeah, these are the values given by the model. So now, as we know, now we'll be predicting on the test set that we have. So we have linear regression and predict on the X test and save those values in the Y predictions. And to compare the values of the actual and the predicted values, we'll be creating a data set called test prediction DF, or test pred DF. I will be speaking test prediction DF just for the clarity of it for the session. So the test prediction DF will be having the values of actual value from the Y test, the predicted values, which will be rounding up for the rounding up to 2 decimal places, and the residual values of the Y test and the Y predictions that were made. So when we predict, when we display those values in the data frame of the data frame, these are the kind of values that we get. These are the actual, predicted, and the residuals of the error relating to the. So as we have made trained the model here. We got the values. We made the predictions. Now we will be checking how much accurate are our predictions. So we'll be checking the accuracy regarding the model that we have built. So we have asked values. First we will be using is the R2 score. So scikit-learn's matrix has this R2 score. So matrix.R2 score helps us to get the R2 values. So what we'll be doing it, we'll be passing the values of Y train and the predictions that were made on the X train. So our R2 value comes out to 0.90, which means that 90% of the variance in Y. just a second. So next is the mean squared error or root mean squared error. There were two metrics that we were going to use. One was R squared value and the root mean squared error. The root mean squared error is the mean squared error is also present in the matrix package of library. So we will be calculating the test. We will be calculating on the test data. So we have the y test and the y predictions that were made by the model. And in the end, to calculate the root mean squared, we use the numpy square root in order to calculate it on the MSE value that we get and rounding it up to 2 floating points. So our root mean squared error value is 1.95. So the model shows the model predictions having standard deviation of 1.95. To improve the model, we need to understand the components of the error term and how to deal with those components. So as that so statistically speaking, there is we are already predicting the values of randomly initialize the values of bias. Then we found the optimal values of bias that we can find for the bias, and there is constantly that we are discussing regarding the variance that is present. So this bias and the variance, they both are connected and they do have a trade-off between them. So the model errors that are present are the bias and the variance. The two components that can be controlled is the bias and variance. So knowing them helps the model accuracies and avoid over and underfitting of the models. And the high bias can lead to building underfitting models, whereas high variance can lead to the overfitting models. So, uh, so uh, we'll be using another dataset called curve.csv. We'll be reading it, and these are the x and y values regarding uh, from the records. So you can see that when we plot this scatter plot from the curve.csv dataset we got, you can see that we are not having a linear relationship for the x and y, as there is a certain kind of curve going on for the when we plot these values. Which means that instead of a linear relationship, there will be a certain degree to the relationship. So a polynomial relationship is present, as we can see from the shape of the plots that we can see. So in order to recognize this, there is something called as a method called as polyfit. Now polyfit takes in the value of the degree for the for this relationship, and give us the when we fit it with the data that we have, it gives us the relationship and how the model is able to predict it or not. If my uh, explanation makes it confusing, once you see the graphs and stuff, you will get a clear idea of what it is. So Polyfit, it takes x and y values and the degree of x features to be used to fit a model. Degree 1 means it's a linear one, and only value of x is used to predict this model, whereas if degree of 2 means x and x square, both of them will be used to predict the values of y. A generic method called fit poly, which makes a degree as a parameter and builds a model with a required polynomials term. So what I wanted to say is that the function custom function fit poly is used, which will be taking in degree of the polynomial. So for that, we'll be using the polyfit method using the x and y values and the degree. Now the curve fit column, the variable of p and the curve dot x is used. To draw the regression line, we use the rig plot from the cbounce library. And return the values of the plot, yeah, plt.plot for a curve fit and the label fit. So basically what I meant with degree 1 is that all the power of the equation will be 1. So the fit poly for the value of degree 1, you can see that there is the line, a regression line that's forming on the graph, and the data is not fitting well. As you can see, the data is not nicely coming around the regression line. So that so it means that the model is not able to understand the data uh, data correctly with the degree value of 1. So model has an underfitting or bias issue, as it is not able to learn the data from its form. So we increase the value of the degree now. For the value of degree 2, you can see that as it's not a linear relationship, a non-linear relationship is able to be represented quite nicely with the degree value of 2. And you can see also it's a functional form. So we'll be trying to use or increase the value of degrees from 2 to 10. But this has a problem of having our model having the problem of overfitting. So an underfitting model has a large error because of high bias, and an overfitting model has a large error because of high variance. So an optimal model will be somewhere between an underfitting and an overfitting model, and will have low bias and low variance. This can be observed by comparing the root mean squared error in the training and the test sets. So remember that when we started, it was underfitting. Now it's overfitting. So in order to find the optimal value for the degree, we'll be comparing the values of root mean squared error on the training and the test set. So basically what we are doing over here is that we are defining something called get root mean squared error, and iterate through the degree 1 to 15 or 1 to 14 basically, for all the values of the degrees that it can have. So these are the values that we get for the root mean squared error df, for the degrees, for the train set and the test set. When we plot the graph comparing the root mean squared error on the training set and the test set, we can you can see that we get the test set of something that looks like this, and the inferences that we can make is that the errors were pretty high when it started, but then it with the increasing number of degrees it started to move down, and after a specific point you can see that around 5 that the error started rising, and for some it kept reducing also. So test errors are high for a degree 1 to 15. The test errors reduces at first and rises continuously. Then training set errors are continuously decreasing. But the test error is increasing after 5. So for us, the optimal value that we can decide, what we can say is 5. As the test error starts increasing after it, we can say it around 5. So the degree can be associated with complexity. It can be observed that as complexity or the number of polynomials terms in the model increases, the model starts to fit to train and test the data well. But beyond a specific level of complexity, as we have seen over here for the model degree value of 5, after that, the test error starts to increase again. So and that is the point where the model starts to overfit and the training set and stops generalizing. So our optimum value will be 5, which has a low bias and the low variance. So for all the linear regression model that we have made, we made it using the scikit-learn. We split the data set, and we basically check the number of records that are present, which is 140 and 140 and 60. For the train and test, basically 200 records in total. Then use the linear regression model from scikit-learns and fit the model for the x and y value of the train data split. When we try to get the intercept value and the coefficient values of it, 2.7, and these are the values for TV, radio, and newspaper. We combine. We basically use the zip function to get the values together for TV, radio, and newspaper, and make the predictions on the X test and save it in the Y predictions. Make the test prediction DF, and you can see the actual values and the predicted values over here and the residuals it has. Next, we have we made the model. We basically decided the model. We decided with the independent variables and the dependent variables. We predicted using the model, and now it's time to check the accuracy of the model. So for that, we will be using the root mean squared in the error and the R squared. So the R squared value is 0.90, which explains that a model is able to explain 90% of the variance, and the root mean square error we get is 1.95. Then learning. So as we discussed that there is a basically a trade-off between the bias and variance. So in order to understand this bias and variance, we used another data set called cow.csv, plotted the values using the scatter plot, and by the looks of it, we understood that it's not a linear relationship. So we define a function called fit poly, which takes the number of degrees of the polynomial, and within that we used a polyfit, which takes the x values, y values, and the degree used. So for plotting the graph using fit poly degree 1, we get this value of regression line. So we got this basically this regression line, which is not able to explain the data set quite well because of the degree that is it is limited to, but a higher degree shows us a better result and better fit to the data. A more higher degree sets to the data very well, and because of that we wanted to find which one is the optimal value. So basically what we did was define the root mean squared error for the y and y fit values, and iterate through different degrees from 1 to 14. So the given range is 1 to 15. So for the different values, this is what we get. So after this, we compare it with the root mean squared error of the training set and the root mean squared error of the test set that we got. So you can see that both training and test set starts the error starts to decrease for both of them. For then around degree 2, it keeps on decreasing, and around degree 4. So yeah, at degree 5, the test set as well as the training set, both of them were declining. But after degree 5, the test set starts to increase again, while the training set keeps on reducing the error. So, and because of that, we decided to go with the value of 5 for the degree. Now, in order to get this, where we don't have to deal with or we can avoid overfitting or underfitting, k-fold cross validation is a very solid approach in order to avoid it. So basically what k-fold cross validation is, let's say that there is a data set, you get a k value. So here the k value is 5. So it divides the data set into 5 parts and uses one, as you can see in the image, that for iteration 1, out of the 5, it takes 1 as the test set and other as the train set, and it will keep on learning the data for all the 5 iterations that it has. So the k-fold cross validation can avoid the overfitting problem by building and validating multiple models by resampling multiple training and validation sets from the original dataset. So the following steps that are used in k-fold cross validation: the split training dataset into k subsets of equal size. Each subset will be called a fold. So as we have taken k equals to 5, so until f5 and I equals to 1 to k. So the fold fi is used to as validation set, and all the remaining k minus 1 folds are training set that train the model using the training and they calculate the accuracy of the model in fi. So the final accuracy obtained by averaging the accuracies across all k models on test data reflects the model performance in the real world, while variance of these accuracies indicate model robustness. So to summarize this session, we started with the discussion of AI ML, the relationship between them, AI ML and DL. Then we discussed few points on the supervised and unsupervised learning. We discussed about the cost function that is associated in so because supervised learning has we already know the outcome value and the predictions are made by the model. There is a difference, so that is the reason why we defined why we discussed cost function. Then we discussed gradient descent, which is an optimization algorithm to minimize the cost function. First, we tried to understand the linear regression and gradient descent with the help of a model purely built on numpy. Then we built a model using the scikit-learn linear regression model, measured its accuracy, and in the end, there we discussed about the bias and variance trade-off with another data set called curve. So we use the polyfit uh, which and define our own function called fit poly, which takes in degree of the polynomial, and found out and plotted different graphs for it, like this one, for a different number of iterations, and sorry, different number of model degrees with the with their performance being compared on the test and train split and the error on the y-axis, and getting the optimal value for the model. So this is it for this session 10 on advanced machine learning module 6.1.
Thank you, Jamit, for the excellent presentation, and look forward to the next presentation. And I will just stop the recording here.